Hello, welcome to my talk for the Geometry and Topology webinar. First, I would like to thank the two organizers, Giuseppe and Ariel, for inviting me to speak in their seminar. I hope it's a great success. So in this video, I am going to tell you about a paper that me and Neja Jaeger-Koreniak put on arXiv last year about proper affine actions in higher dimensions. So the main theorem that I want to sort of tell you about is this one. So I want to state it at the beginning, but I will not assume that you know most of these words, and we'll explain everything later. So what we prove is that if you have a compact surface with at least one boundary component, and then you take a representation of the fundamental group of that surface into a split orthogonal group of signature 2n, 2n minus 1. There's a condition on such representations called positivity. So if you have a positive representation, and in addition you ask that it's an Azov, which ends up just meaning that the boundary components of the surface, the boundary loops are mapped to elements that fix two flags, then it admits a proper affine deformation. Okay, so let's talk about a little bit about what these things mean. So if you have a vector space over R, an affine action of some discrete group on, okay, it doesn't need to be a discrete group to define an affine action, but in this talk, we will only be interested in discrete groups acting on finite dimensional vector spaces. So it's just an action on V by affine transformations. So the affine group can be written as a semi-direct product of the general linear group with the vector space itself acting by translations. Now, if you have an affine action, you can ask for it to be proper. What properness means intuitively is that when you go to infinity in the group, you go to infinity in the space. The technical definition is that this map F, called sometimes the shearing map, which maps a pair gamma V of an element in the group with a vector in the vector space to the vector itself not moved in the second entry, and the action of the element on the vector in the first entry. And you want this map to be proper, meaning that the preimage of a compact set should be compact. Now, the general question that is of interest is, okay, which groups can act properly on a given vector space, and what are all the possible homomorphisms? So you want to classify these actions if possible. So the motivation, the history of this, comes from crystallography. When we talk about at least the classical subject of crystallography, the one that has sort of, you can say it has applications in physics maybe for classifying the possible shapes of crystals in any dimension, then you want your transformations to not just be affine, as in the previous slide, but you want them to preserve distances. And moreover, you want the quotient of the vector space by the image of the group to be compact. So an example of this is this picture. This is a salt crystal. You can see here that the group acting is just, well, you can have multiple groups acting. But OK, if you do there's at least Z3 acting by 3 linearly independent translations. You can think of moving the green atoms to each other by translation, and the purples to each other by the same translation. And you can also see some reflection and rotation symmetries in this type of crystal. So this is what motivates the subject. Now, in the case of crystallographic groups, so these actions of discrete groups with co-compact quotient and by isometries, there's a very nice result by Bieberbach, which says that any group that acts this way needs to contain a finite index lattice. So basically, it looks like this one. and it needs to have a lattice of translations in it of finite index. So lattices in isometries of Rn are just Zn, basically. So n linearly independent translations, group generated by those. Now, okay, say we want to look at the more general problem that we stated before, so affine actions that are proper. Let's look at the super baby case, right? So dimension 1. In dimension 1, all elements have a fixed point except the translations. So if you look at any element of the affine group of the real line, it will fix some point, or it will be a translation. And when you want to have a proper action, as I said before, you want, when you go to infinity in your group, you want to go to infinity in your space. So you don't want to have fixed points, at least not for infinite order elements, right? So when you have a proper action, it it needs to be essentially to consist of only translations. So up to finite index, the only group which can act is Z, because if you had two translations which generate, for instance, a Z2, you would also contradict properness, because you could. I mean, if the two translations are not rationally related, then you can accumulate around any point in R. So now, when you think of dimensions higher than 1, one thing that becomes useful is the Tits alternative, which says that when you have a linear group which is finitely generated, so all the groups that we will be looking at here are finitely generated, and they are subgroups of a linear group because you can put the affine group inside the linear group of one higher dimension. The alternative says that there's two possibilities. Either gamma is virtually solvable, or it contains a free subgroup of rank 2. Now, the Auslander conjecture, a very long-standing conjecture in the subject, says that or claims that all discrete subgroups which act properly and co-compactly by affine transformations are virtually solvable. So it's sort of an analog of the Bieberbach theorems, but for affine transformations. And instead of saying that they're virtually lattices, it says that they're virtually solvable groups. Now, when thinking about this question, there's also a fairly old complement to this conjecture, which was a question asked by Milner. What if you just dropped the co-compactness condition, which is what I did at the very beginning when I talked about proper affine actions, right? I defined them just as a group acting properly on the vector space. So maybe this conjecture is even true when you don't ask for the group to act co-compactly, but just act properly, right? So we'll see. It turns out that the answer to this question leads to very interesting places, among other things, to the paper that we wrote. So in higher dimensions, the affine transformations that have no fixed points are exactly those that have 1 as an eigenvalue for the matrix part, right? An affine transformation has a matrix and a translation. And if you want to have no fixed points, you need to have 1 as an eigenvalue. It's not to, I mean, you just write down what it means to have a fixed point, and you end up with the equation for having not having 1 as an eigenvalue. Because this is an algebraic condition, this means that there's some algebraic subgroup H of GL and R, which contains the linear part of our affine representation, all of whose elements also satisfy this having an eigenvalue of 1 condition. And for dimension 2, Fried and Goldman showed that this is enough to rule out any proper action by a non-solvable group. These are examples of proper affine actions in dimension 2. You have sort of the Euclidean ones, where you have translations in linearly independent directions, but you have slightly more complicated ones where you conjugate the left picture by a degree 2 polynomial, and you get weirder tilings that are preserved by a discrete group of affine transformations. Now, what happens in dimension 3? So this is where it starts to get interesting. In dimension 3, Fried and Goldman showed that this eigenvalue 1 condition, which is also what we used even in the R case, right? Like the important thing was that your linear part needs to be 1 in order for you to not have any fixed points. This was what I said when I talked about the R case. So this turns out to be a really important condition in every dimension. So this condition, together with non-solvability, means that the linear parts of your groups acting by proper transformations need to preserve a quadratic form of signature 2-1. So the only subgroup that can sit in between the linear part of your group acting properly and GLN, or GL3 in this case, is some SO21 for some quadratic form. Now, SO21 is one of the several isomorphic groups that describe the isometries of the hyperbolic plane. So this is not a trivial thing, but when you have a proper action on R3, so we said it preserves a signature 2-1 form. Yeah, I mean, its linear part preserves the signature 2-1 form. It turns out that, moreover, it has to be discrete, and so virtually it's the holonomy of some hyperbolic surface. Margulis found examples of free groups of rank 2, which act properly on R3, answering Milner's question in the negative for dimension 3. So in dimension 3, there do exist non-abelian free groups which can act properly by affine transformations. They're not easy to construct or understand. One way to visualize what they look like and understand them was found by Todd Drum. It's called crooked planes. And you use crooked planes, these surfaces that you can see in the picture now, to form a fundamental domain. Or in other words, you can subdivide R3, like in the picture, using crooked planes into tiles that are permuted by some affine group, some group of affine transformations. So I will show you maybe in a little bit more detail here. So this is, in this example, the group that's acting is generated by 3 reflections. So it's like a free product of 3 copies of Z2. So from the top here, so these are crooked planes. From the top, and they all intersect at the origin of R3 here. From the top, you can see sort of the beginning of a tiling of the hyperbolic plane, which would be this circle here, by triangles. So there is this central triangle and then a few neighbors. And now, when you want to construct an affine action, this is just a linear action on the hyperbolic plane, which I visualize in R3. And you have some parameters here, which let you pull them apart. And when you pull the crooked planes apart, it means that you have to add translations to your group. And when you do that, you end up with disjoint surfaces. Oops. Disjoint surfaces which tile all of R3. Okay, it's not super obvious because I only drew the beginning of a tiling. This is the same picture that was in my slides, but I can rotate it. And you can convince yourself that all of these surfaces are disjoint from each other. And there's some affine group. In this case, it's pretty easy. The affine group is just generated by reflections in 3 of the crooked planes. This is why I colored them. So you have a reflection in the blue one, which swaps its 2 sides, a reflection in the green one, and a reflection in the red one. And you just take the affine group generated by these 3 reflections in surfaces that don't go through the origin, so they're really affine reflections. Okay, let's continue. So these were the first examples of actions, proper affine actions in any dimension, really, by a non-abelian free group. Story does not stop here. So one question is, all right, okay, we construct this by starting with a linear part, which has to do with a surface, and then adding translations in the right way to get a proper action. But this doesn't really tell you why, like, how, what's the relation between this affine action that we constructed and the hyperbolic surface, right? So this came a bit later. So in dimension 3, one of the key invariants is the Margulis invariant. When you have, so here, this alpha is a quantity that you associate to some affine transformation. The affine transformation is given by two things, a matrix and a vector. The matrix is some element of SO21. And what you do is all elements of SO21, as I said before, have a 1 as an eigenvalue. And so they have an eigenvector, a real eigenvector of eigenvalue 1. And there is a way to orient it canonically given the element A. So A0 here in my slide is this neutral direction for the element A oriented in the canonical way and normalized. And then the Margulis invariant is just so the dot product here is the Lorentzian signature 2-1 dot product coming from the preserved quadratic form. When you take this product, you get an invariant of the affine transformation. And this invariant tells you something about properness because, among other things, when it's 0, your element has a fixed point. So one important thing is that this invariant was reinterpreted by Goldman and Margulis as a derivative, the derivative of a length function on a hyperbolic surface. So what do I mean by this? If you have a path of representations, so you take your fundamental group of the surface, you take a path of holonomies of hyperbolic structures on this surface, then its derivative, turns out, has exactly the same structure as what you need to make it into a representation of the affine group. It's a cocycle for the adjoint representation. And in dimension 3, or for the group SO21, there's this miracle where its Lie algebra is the same dimension as the linear vector space on which it acts, and the adjoint representation is just isomorphic to the linear representation of SO21 on R3. So you get an affine action whenever you take the derivative of a path of representations like this. And so this is what I meant in the previous slide by this Margulis invariant can be interpreted as a derivative. When you have, so on the space of all representations of the fundamental group of your surface into SO21, you have functions. For instance, you can fix a curve, gamma, in your surface, and you can count its length and its hyperbolic length. And this length will change as you move around the space of representations, or Teichmuller space if you want. And if you take the derivative of this function in the direction of a vector, so this vector will be given exactly by a cocycle, so will correspond to some affine action with linear part rho 0. And the derivative of the length function is precisely the Margulis invariant. So I hinted at this a little bit before when I said that the Margulis invariant had something to do with properness, because it detects when elements have fixed points. It actually has a lot more to do with properness. So the succinct way to say this is if you have a hyperbolic surface, you fix a holonomy of a hyperbolic surface in SO21, then you can look at its tangent space in the space of representations. So we'll just look at all directions, all possible directions in which you can deform it. Some of those directions will be proper affine actions. And it turns out that the proper directions are exactly those which lengthen every closed curve uniformly. You can also say it as shorten every closed curve uniformly because, so this is not quite correct. Either they lengthen uniformly or they shorten uniformly, because when you have a proper action, the negative of the cocycle is also proper. So one way to uniformly lengthen a hyperbolic surface, this is a picture shamelessly stolen from Neja's thesis. You choose an arc in your hyperbolic surface, an infinite embedded arc. You cut along it. So this is the second picture. And then you glue in a piece of the hyperbolic plane, as in the fourth picture, inside your surface to make it bigger. This will lengthen all of the curves that are transverse to this arc. And if you do this with enough arcs, then you get a proper affine action. This is the culmination of this is this theorem by Danziger, Guerito, and Cassel, which says that actually you get all proper affine deformations by doing these strip deformations. So you choose enough arcs, you fix some combinatorial data associated to each arc, and then all of the proper affine deformations of your fixed linear part, your hyperbolic holonomy, are given by doing like gluing in arcs on gluing in strips at each of these arcs simultaneously, and doing this infinitesimally, because remember, we don't actually deform the structures, we just point in a tangent direction. So in higher dimensions, now we leave dimension 3 and we ask, okay, the question is basically answered in dimension 3 through these strip deformations. What happens in higher dimensions? So the first result in this direction is Abels, Margulis, and Seufer in 2002, which proved that when you look at proper affine actions of the free group of rank 2, it can act on R P plus Q with linear part in a split orthogonal group exactly when the pair PQ is of the form 2n, 2n minus 1. So this is the same number that appeared in my first slide. And when P and Q are not of this form, then there can be no proper affine action of F2 with linear part in that group. So later, a little bit later, Ilya Smilga showed that for some of these actions, so this is only an existence result, right? It doesn't tell you how many there are and which linear parts are possible and how many translation parts are possible for each linear part. And Ilya Smilga proved that if you assume that your generators are sufficiently contracting, then you can say a little bit more about the topology, just like in dimension 3, by constructing fundamental domains that are bounded by hypersurfaces. Ilya called them tennis ball domains. So our goal in the paper that I wanted to tell you about is to sort of go a little bit further than this and say something about say something for a large class of possible linear parts, instead of just saying that there exists some proper affine action of F2, we wanted to say, okay, let's assume that we have more structure on the linear part, and one thing that gives you a lot of structure is positivity. So these positive representations are a special class of representations of the fundamental group of a surface into a real split Lie group. So you can think SLN R. So the way these are defined is when you have a surface of negative Euler characteristic, then you look at its universal cover, and its boundary will naturally embed in a circle. You can, for instance, fix a hyperbolic structure on it, and then it will its boundary at the boundary at infinity of its fundamental group will embed inside the boundary at infinity of H2, which gives you a cyclic ordering on the boundary. Positive representations will be defined in terms of this cyclic ordering. So what you do is, in your Lie group, you need to have this additional structure, which is called a theta positive structure now. So on some partial flag manifold, you define a notion of positive triple. So it tells you basically when a triple of points in the flag manifold is ordered in the right way, and this is similar to the cyclic order on the circle. This generalizes the case of SL2R. So if you quotient SL2R by the upper triangular matrices, you get the circle, and the circle has a SL2R invariant cyclic ordering. And this is the same as the one on the boundary of H2. It turns out that there's something like this in SLNR for every n, but the cyclic order is a bit weaker in the sense that it's more like a partial order. So not every triple of flags is either positive or negative, as in the circle. Sometimes it's just not neither. But you can still define positive representations using this. So you take a representation you say is positive if there's some curve from the boundary at infinity of the group into this partial flag manifold, and it sends positively oriented triples to positively oriented triples according to this positive structure in G mod P. So for example, if you take a discrete and faithful representation into SL2R and you compose it with the irreducible representation of SL2 into SLN, then you always get a positive representation. And the curve which is positive, really the sort of model curve for all positive curves, is the Veronese curve. And here I say curve because I sort of have in mind the case of a closed surface, but since we're looking at actions of free groups, the surfaces we're looking at are really open surfaces or surfaces with boundary components. And so the curve is a Cantor set sometimes when your surface is not closed. So the idea that we had was we understand in dimension 3 that these strip deformations, these infinitesimal strip deformations, give you all possible proper affine actions of the surface group. So we wanted to do this in higher dimensions. And if you have positivity of your linear part, it gives you a lot of structure related to the boundary of H2 because of this positive map, this positive boundary map. So what is an arc? Well, an arc in a surface, if you lift it to the universal cover, really what it does is it gives you, the idea is if you lift an arc in the surface, it will give you an infinite family of arcs in the hyperbolic plane. And each of these gives you a pair of points in the boundary of H2. So in general, the endpoints of these arcs are not going to be part of your limit set or of the boundary of your group, but you can still pick flags related to your Cantor set limit curve in the right intervals. So basically, you take this map that gives you for all the points in the limit set of your linear part, it gives you a flag. And you can add more flags to this, but you add them carefully so that they land in the right interval to sort of extend this boundary map to a map that also includes the endpoints of arcs that you've chosen to cut up your surface. So the idea is for each arc, you get a pair of flags. And then to this pair, you can look at the one-dimensional part of each one. And there's also a way to orient all of the flags so that there's a unique orientation. And then you choose some translation that has a non-zero component in the direction of F1 and a negative non-zero component in the direction of G1. And this is enough. This is basically the same as what, if you specialize to n equals 1, you get SO21, and you get the same infinitesimal strip deformations as Danziger-Guerito and Cassel. So, but this also works in higher dimensions. So whenever you have a representation here, S should be a surface with at least one boundary component, as in the introduction. So this is a free group. Whenever you have a representation which is positive and an osov, the reason why I write it as pi1 of S and not as a free group is because you don't get the same notion of positive when you pick a different surface. So the ordering on the circle depends on which surface you chose. For F2, it's either a one-hole torus or a three-hole sphere, pair of pants. And those give you different orderings on the boundary at infinity, and so different notions of positive representations. Now, whenever you have a representation like this, then you can construct a cocycle as above by using strips, choosing flags, associating translations to each of those. Then we call them higher strip deformations, and we get proper actions for every possible linear part which is positive in an OSOV. And one thing that it has, one thing that our result has that wasn't already proved by Abel's Margulis Soifer and Smilga is that we have no assumption really on the contraction strength of the elements. We only assume that they're positive, and positive representations, if you look even for just SO21, all discrete faithful representations are positive representations. So you can get hyperbolic surfaces that have very, very short closed curves in some directions. And similarly, you can get positive representations which don't contract very strongly. It's not possible that all of your elements don't contract, but you don't have to assume that everything is very contracting, which is sort of nice. It's more geometric rather than sort of dynamical, assume that everything is super contracting. Here's how this works. So if you have a surface here with at least one boundary component, you choose some arc or some system of arcs. Then it will have multiple lifts to the universal cover here, the hyperbolic plane. So maybe the lifts look like this. Okay, some set of lifts of this curve. Now you choose some element of the fundamental group. So you have a base point. You fix a lift of this base point here, P0. And you pick an element of the fundamental group. Maybe it goes here, it's behind, it comes back here, and then back to the base point. Okay, so this is your element gamma, and the goal, so this element gamma is something you can apply your representation to. You have rho of gamma, which will be a matrix, and you want to define U of gamma to be some translation that you add to this matrix in order to make your group into an affine group. So you want to define this cocycle U. That's what we're trying to define. So you lift this gamma to the universal cover. Maybe it looks like this until it hits gamma of P0. And for each crossing, you will add some translation vector, and you sum of them, you sum over all crossings. So in this picture, I have two. And each crossing will give me a pair of points in the boundary here, to which I associate flags using the boundary curve. So maybe if this arc is called A, it comes with some orientation, which I didn't talk about, but the curve crosses it in some orientation, and so you can distinguish between the point on the left and the point on the right. Maybe call this one A minus and this one A plus. And the cocycle will have a part which is in the flag C of A minus 1 minus C of A plus 1. So these two are flags associated to these boundary points that we've added to the boundary map. And then for the second crossing, maybe this arc is B, you would have another, you would add another vector and subtract another vector for each of those two endpoints. And this is how you construct the cocycle U, which is the higher infinitesimal strip deformation. Also, because crooked planes, these piecewise linear surfaces that I showed earlier, are sort of very intimately related with strip deformations, in some sense, a strip deformation gives you a way to construct a fundamental domain with crooked planes. We do the same thing in higher dimensions. We have a notion of higher dimensional crooked planes that works in R2n to n minus 1, and they give fundamental domains for these proper actions associated to any positive Anosov representation of a free group. So in particular, we get that the quotient is always a solid handle body, same as the Smilga result, but it doesn't tell us, unfortunately, what we can't do is the whole thing with the arc complex, because we don't understand as well what the geometry of the space of cocycles looks like. So it would be very interesting to know if all possible affine deformations, proper affine deformations of a positive representation in higher dimensions can be obtained with this construction. I think right now I believe that this is not true, probably, but I don't have any counterexamples as a direction in which we're looking for the future. Thank you very much for watching, and I'll be looking forward to answering your question at the coffee hour later this month.